And firstly, we have Ana Silva talking about graph problems arising from temporal graphs. So take it away.
Thank you. Okay, so I am Ana. I am actually a graph theorist by formation, and I stumbled upon temporal graphs working with Andrea Marino from University of Florence. I am from Universidade Federal do Ceará in Brazil. I'm actually on vacations, trying to, but also part of the group Pargo, which is called Parallelism Graphs and Optimizations. And I thank the organization for inviting me. And sorry for before, I was just organizing some stuff. Okay, so today I'll be talking about on graph problems stemming from temporal graphs. The idea of this talk is kind of, since like I told you, right? The talk is about this, trying to put together these two things, and sorry, just a second. And I'll bring you two problems on which I work, that one of them brought from graph theory a result on temporal graphs, and vice versa. The other one, which I liked more because I am a graph theorist, so brought a result from temporal graph to graph theory. So I'll be talking about these two things. I hope it will be understandable, but feel free at any moment to interrupt me if I start to talk too fast. Okay, so in order to talk about this, first I need some basic definitions. We know that there are many notations around there. The notation that I will be using is this one. A temporal graph is a pair G lambda, where G is a simple graph and lambda is a function on the natural number of the edges, into subsets of the natural numbers. As an example, we can see this temporal graph. This edge here will be active in time 1, this other one time 1 and 3, and so on. I will also be calling a snapshot the subgraph of the base graph G here, active in time I. So, for example, you'll see more, a lot of figures, because I like to work with figures and also formal definitions to help everyone. And so sometimes I will be, instead of denoting the graph like this, I will be denoting as a sequence of snapshots. And the sequence is finite, so this means that there is a maximum value in which a given edge is going to be active. And I'll be calling this maximum value the lifetime of the graph and denoting it by tau. Okay, some more definitions. A temporal vertex is nothing very special. It's just a pair, a vertex and a time. And a temporal edge is going to be an edge with a time, but this is a little bit more special because the time must be one of the times in which the edge is active. So, for example, this edge here gives rise to two temporal edges. The first one, xy in time 1, the second one, xy in time 2. Finally, I will be calling a dynamic-based graph a graph that is just always active. So the function lambda is equal to all the step times, right? From 1 to tau. Okay, so the first problem that I want to talk about is temporal coloring. This problem was introduced by Matthews, Moulter, and Zamarev. And here we want to minimize the number of colors needed to color the temporal vertices in a way that every edge is properly colored at least once. A lot of things there. What means properly colored is just that at some point, the edge, the two endpoints, at some time step, the two endpoints of the edge is going to have two different colors. So let's see an example. If I give this two coloring to snapshot G1, then in the next snapshots, I don't need to color anymore XY, nor SX, nor YT. So these three edges are going to be solved already. And if I give this coloring to snapshot 2, then I don't have to care about this edge anymore, UX, right? And finally, I can give this coloring with two colors to snapshots 3. So this means that I have used two colors to temporarily color this temporal graph, and the minimum number of colors needed to do that is going to be called temporal chromatic number, and I'm going to denote it by Tchi G lambda. Okay, so this is the problem in which we studied, the problem that we studied on temporal graphs, and now I'm going to talk about the problem on static graphs that I thought that there was some relation. So we say that a graph is k-partite if it can be properly colored with at most k colors. In this example, we have a complete graph on the vertices. So if you want to give colors to these guys in a way that that the two endpoints of each edge is going to have distinct colors, then this is going to need 8 colors. So this means that this graph is 8-partite, but it's not the problem that we're working on. That we'll be looking at is this one, a little bit more complicated, that is called k-partite cover of G, which is a collection of subgraphs H1 to HT, such that each HI is k-partite and every edge belongs to at least one HI. Okay, also again, a little bit weird and complicated definition, but let's see an example. So this here is a 2-partite cover of the complete graph. So let's see if this is true. I have here picked a 2-partite graph that is also called bipartite sometimes. And this bipartite graph already covers all these edges that are dashed in the second subgraph. So I need to worry only about these other ones. And I pick this other bipartite graph or 2-partite graph. And this one covers these other 8 dashed edges. And it remains only to color these last 4 edges, which I can also cover with a bipartite graph. Okay, so is it clear what a k-partite cover is? I think so, right? And the minimum number of subgraphs T is the k-partite number of G and is denoted by beta k of G. Okay, so this problem, I have looked around a lot and I found only this paper talking about it. And among other things, they prove that that number, right, the k-partite number of the graph is exactly the ceiling of the logarithm base k of chi of g, where chi of g is the number of colors that you need to properly color the graph. Unfortunately, this paper, I couldn't find a published paper, only on, I don't remember where, but it was on archive, I think, but it was not peer reviewed. So in our paper, we give another proof for this. Okay, so what's the relation among these two things, right? They look a little bit the same because here I want to cover the edges with k-partite graphs, and on the other one, I also want to cover the edges in a way, but we want to respect the time, right, that the edges are going to appear. Okay, but the main difference is that here the edges are always available, and there they are not always available, but we know about dynamic based graphs. So maybe these things are related to each other. So let's just recall a little bit fast what each thing is. So a temporal chromatic number is the minimum number of colors needed to color the temporal vertices in a way that every edge is properly colored at least once. And the k-partite number is the minimum number of subgraphs such that the edges of G can be covered by T subgraphs, each of which is k-partite. And we know that this value, the k-partite number, has already been proved to be equal to this value. As a corollary of this result, we get this. So we get that if G is a graph and T is exactly equal to the k-partite number, and I form a dynamic-based graph, just a sequence, okay, and I give it enough time to cover all the edges, so the lifetime of this dynamic base is going to be equal to T, then I know that the temporal chromatic number is going to be at most K. Very fine, but this is not so useful for this problem because chi of G is a very hard, chi of G is the chromatic number, is a very, very hard problem. So deciding whether you can color with two colors, so deciding whether a graph is bipartite is very easy, but deciding already if you can color with three colors is NP complete. Which means that it is per-NP complete in the parameterized complexity URI. But we know some bounds for chi of G, and this could be useful. Here I gave a very easy upper bound for this, which is n. Of course, if you give a different color to each vertex, then every edge is going to be properly colored. So if you have, this means that if you have a dynamic-based temporal graph with lifetime tau, then you can do some computations, easy ones, to conclude that the temporal chromatic number of G lambda is at most the square root in base tau of n. Okay, so this was the example. Well, we proved other things, of course, but this was the example that I thought was nice, in which we picked a result in graph theory and brought to temporal graph theory. Now I'm going to do the other way around, and I must confess that this is my favorite one because I am a graph theorist, as you know. And we have also worked on temporal Eulerian walks. So in order to do this, I'm going to, again, do the first thing, the first thing that I did in the first part. I'm going to present the problem on static graphs, then on temporal graphs, then try to relate them. Okay, so let's first take a look at what is an Eulerian trail in a static graph. So a trail is a sequence of edges that does not repeat edges. It's a circuit if it starts and finishes on the same vertex. And it's Eulerian if it visits every edge of the graph. So in this example, I can take this trail here. So I can go from X to S, then to U, then to X again, and to Y, to U again, to T, and back to Y. And why I was interested in this problem, because it's a very easy problem on graphs, and actually a quite beautiful one, and the one that the graph theorists are proud of, because it's very old. It's considered to be the first theorem on graph theory. And it says this, that G has an Eulerian trail if and only if it has exactly two odd degree vertices, okay? And between parentheses, if you want a circuit instead of a trail. So again, it's very easy. You can just look at the graph, decide polynomially, are there any odd vertices? Odd vertices mean odd degree vertices. Yes. Are there more than two? Yes. So it's not, there is no Eulerian trail. If there is no odd vertices at all, then it's there is an Eulerian circuit. Okay, so this was the problem on static graphs that we were interested to look at what happens in temporal graphs, right? So we worked on this, and I'm going, well, we did many things, but I'm going to present here only the things that I think are going to fit inside this talk. So a temporal local trail, we picked the definition on static graphs, as we usually do, right? And try to see how they work on temporal graphs, and see the many different ways of formulating it. And we found three formulations for this, but here I'm going to talk only about one of those three. So a temporal local trail is a temporal walk, and I forgot to define what a temporal walk is, but I think most of you here know what it is. It's simply a walk that you do in the temporal graph. And a walk means that you can repeat vertices, you can repeat edges, you can repeat whatever. And in this model, I can use more than one edge in each snapshot. So a temporal walk is this, but a temporal local trail, again, is a temporal walk that forms a trail in each snapshot. Again, looks complicated, so let's look at it. Sorry. And it's Eulerian if each edge is visited at least once. Okay, so the definition like this is not so easy to follow. So let's see an example. And to see it more clearly, I'm going to, again, look at this temporal graph as a sequence of snapshots. Okay, and I do it like this. I go from U to S, then from S to X, from X to Y, then continuing, right, in order to be a temporal walk, sorry. I go from Y to X, then from X to U, then from U to Y. Continuing from Y, I go to T, and then to 8. Observe that this is a temporal local trail because it's a temporal walk, as we saw, and it's locally a trail, right? So here I did not repeat any edges. Also here, neither here. Now let's see if it's Eulerian. Well, it is, because I see that these edges here have been visited in time step 1, these two in time step 2, these two in time step 3, and this one was visited actually twice in time step 1 and 2, but it's not a problem because it's a temporal walk and we are allowed to repeat edges unless you are in a single snapshot. Okay, so this is the definition of an Eulerian local trail. And among other things, we proved that if G is the dynamic-based graph is lifetime 2, such that G has degree at most 4, then deciding whether G has a deleting and local trail is NP-complete. So just to see how, and this is not very surprising, I think, for you, because very easily you come from static graphs and you generalize to temporal graphs, you do your formulations, and most of the times the problem becomes hard. That's why I'm usually, when I try to work as much as I can, right? And the time is finite, so when I can work on temporal graphs, and if it's something that I am bringing the problem, I usually propose a problem that is polynomial on static graphs in order to see how it will, behave in the temporal graph model. And as a corollary, it's not direct, but those interested to see, to know the proof, you can go there and read the theorem. But as a corollary, we got something that for me was surprising and was not known. I've been talking around, did my research, and indeed I didn't find anywhere where this has been proved before. That if G is a graph of degree at most 4, deciding whether the edges of G can be covered by 2 trails is NP-complete. So looking at Euler, right? Deciding whether the edges of the graph can be covered or visited by 1 trail is very, very easy. But now, if you just want to have 2 trails that are not necessarily, they can intersect, right? So you have 2 trails that covers, but they have to cover everything. Then the problem becomes NP-complete, and this was not known in the graph theory community. So basically, that's it. I think that I have, since I have been working with these 2 things, and I always try to do this move, right, to go from graph theory to temporal graph and do as much as I can some research here and there. My final remarks is just that the temporal graphs seem to combine graph theory and also ordering problems. I didn't present the ordering problem that I stumbled upon in another paper because there is not enough time. So I guess it's worth looking for collaborations. That's my final remark between these fields. But I think that a very important thing to do in order to be able to do these collaborations is to try to talk and use the same notation, the same languages. So if you want to collaborate with graph theorists, then it's very interesting that you choose a book that you respect and that you know, and you try to use the words that we use there. It's just a hint because I admit that I have some difficulties sometimes reading the temporal graph papers because they use very different words for things that we already use in graph theory. And I think it would be even more, I think, would be very productive to do that because then these 2 fields could collaborate even more. I have been going out there trying to show temporal graph theory to people from the graph theory community, and I have to use their language, otherwise they will not be interested. So I don't know. Perhaps in the future we will see a conversion, right? I know that also within the temporal graph community, there is a lot of difficulty to use the same notation because I don't think there is a consensus, and it's normal because it's a very new theory, right? It's something that is developing right now, and it's okay as well. That's it, I think, what I wanted to say. Do you have any questions?
All right, thanks a lot for the talk. I think lots of good points about new chances for collaborations. Does anyone in the room or online have any questions? Is there anyone online who? Okay, well, I guess I have maybe a small one about the colorings. So I guess with temporal graphs, of course, and I think we're going to see in the next talk some more discussions about colorings that have a slightly different definition than yours. But there, one of the, and perhaps this is a challenge that follows what you were talking about having more consistent language. But one of the big challenges is that we have quite a lot of different definitions of colorings, and I was wondering if there were any you thought would be worth pursuing beyond just the one about having a coloring such that it's valid for at least one time step.
Sorry, can you repeat that again?
I was just wondering about if you have any thoughts on any of the other versions of temporal colorings that we can might.
Other versions. As I said, I'm actually a graph theorist, and I am very interested, and I'm trying to broaden because all of the theory behind temporal graphs is extremely interesting, I think. That's why I went inside. But I have to admit that that's not my main field. I work more with graphs. So I respect, and that's, I try to adopt some notations sometimes, but sometimes I change them as well because I want to bring, you understand? Like I want to bring people from graph theory and maybe try to put these two fields together. It's my, for now, it has been my effort.